Let's get started. It's a little over 4 o'clock. The lecture is between 4 and 5. Thank you all for coming. My name is Shaowen Wang. I'm a professor in the Department of Geography and Geographic Information Science within the School of Earth, Society, and Environment. It's a long title for the unit, but it's all hosted here. So, and I'm very delighted to help kick off our campus Geospatial Data Sciences Distinguished Speaker Series today. And this is sponsored by the Office of Provost and also co-sponsored by a number of campus units reflecting the cross-cutting nature of geospatial data and geospatial data sciences. The speaker series is a whole year long, the calendar year, and we're live streamed. So if you go to go.illinois.edu/geodata-science, this is your link for seeing the video as a stream. If you're on Twitter or any other social media outlets, feel free to share with your friends and colleagues if they're not in the room. And this link will be active for the whole year. We'll get around 7 or 8 additional speakers in the Distinguished Speaker Series for the whole year, so stay tuned. There's a book you see getting passed around, making sure you register name and emails on the book so that we will include you in the future speakers events. So now, it's my great honor and pleasure to introduce the first speaker of this Distinguished Speaker Series, George. First of all, George and I known each other for a long time. For geospatial folks in the room, he really needs no introduction. Since we know each other, I'm going to say a few words about George.
Uh-oh. That sounded ominous.
He obviously has long distinguished career, and he's a proud alum. He did his bachelor in engineering physics here, and his master's in electrical engineering. And he mentioned to me he had lots of fun with Plato. If you still remember that, which apparently is the first ever computer-assisted instructional program on this planet for multiple decades of success. George, after going to his career advancement, had really lots of fun cutting across industry and the government sector, and quickly demonstrated not only his technical skills, but also his leadership skills. And he's really amazing able to do this across 2 major sectors with very rich experience. He's currently the Chief Technology Officer and the Chief Engineer of Open Geospatial Consortium. And for those of you who are not familiar with OGC, is a really influential organization with over 500 member institutions. And you certainly know, for instance, Google is a member, and major federal agencies in the US, such as NASA and USGS, and lots of well-known universities across the globe. So this is an organization of developing standards and best community practices for linking very massive, sophisticated system components to make accessible geospatial services. And George is having the very high reputation being the person to go for getting things done in this organization, in fact, across his career. Another thing I just quickly mention about George is his very broad impact in the geospatial community, serving so many different roles, including a few one. For instance, multiple years back, he served as an advisory committee member for our CyberGIS Center, and more recently as also external advisory committee member for our NSF project to conceptualize National Geospatial Software Institute. So his footprint is all across the map, and it's so generous for George, and we are very grateful for your visit. And I think your title is very intriguing to us. Look forward to hearing your insights. And the floor is yours. Thanks very much.
Thank you. Thank you. So appreciate that overly gracious introduction, Xiaowen. It has been my pleasure to work with you over the past bit. The microphone work in the back, people in the back in here? Good, good, good. And it's a real pleasure, of course, to return as an Illini alum and see the state of the university is healthy. So many people are excited about Illinois and are making good progress coming out of here. Kind of a sense of the room with respect to the topic area. I would imagine some of you are more computer science, some of you are more geography. So who's a computer science kind of leaning? Okay, yeah, and geography kind of leaning? Yeah. So, okay, so that gives me a sense of that. So let me speak about this topic. It is an area very much of an interest, and it relates to, let me give you my perspective then, from computer science, geography, that kind of stuff. Physics degree, went into remote sensing, weather satellites at a company that no longer exists called Hughes Aircraft, Howard Hughes kind of thing, and the system engineering associated with those. System engineering may not even be something most people recognize. It's planning ahead for stuff now. It's kind of the opposite of what we do sometime in software. We go scrum it out. System engineering is more about planning up front. And so I often refer to myself as a reformed system engineer in that regard. Worked on GOES and GMS initially, and then worked on EOS DIS. Found out we have some good history of doing that. And then that led me to the whole project was about, here are these 60 COTS software projects. And your job as chief engineer of this release is to put these 60 COTS projects together like Lego blocks, and it'll all work, right? Well, there's only one problem. Lego blocks have uniform interfaces and are designed to be plugged together. At that point, there was no real standards for the interoperability of geospatial software. And so plugging together those COTS products, that's software products that was given to us to build this. Back then, it was going to be 3 petabytes in the 90s, and that was a whole lot of data back in the 90s. And so my takeaway from that was we needed standards to be able to achieve the information systems that we wanted to build associated with Earth observation data and geospatial data. And so I joined this organization called Open Geospatial Consortium. It's a not-for-profit that's all chartered to do these kinds of things. A global forum of developers and users of spatial data products and services, open international standards for geospatial interoperability. So I found a home. I also love maps, and so it's kind of a fun thing to do, to draw maps. So I know all the geography folks love maps, right? So, to some degree, we have solved that problem. To a very real degree, we have solved that basic geospatial interoperability problem. There's existing set of open standards that are implemented by every GIS company on the planet, and they are used in operational systems around the globe in order to achieve access to all kinds of data about our planet and our lives and the people in our lives and the like. So if you know anything about OGC at all, you'll recognize especially these 3 acronyms, WMS, WFS, and WCS. Web Map Service, Web Feature Service, Web Coverage Service. So maps, features, and then coverages. And I'll actually, if you don't know what a coverage is, I'll hit that pretty hard because coverages are a really key data structure for the kinds of analytics and data representation that are important for data science, geospatial data science. And then a set of encodings. KML is the one that Google Earth uses and the like. You may recognize HDF, came from NCSA back in the day. It's now progressing to be an OGC standard and the like, and we've addressed this on many different applications of different activities. But what we're here to talk about today is data science and the revolutions that have come about for that. So when Xiaowen and I began talking about what the scope of this talk should be, and we ended up with a focus on data science, it brought back to me this book. So some of you may be familiar with this book, and this is data science. This group did not invent the term data science, but this is a good book that captures a lot of what was being talked about at the time that these ideas were really gelling in people's mind. In particular, Gray, who was a researcher at Microsoft Research back in the day. It was tragically lost in a sailing accident, at least disappeared. Defined that this was on the slides from his chart. So this progression of science, empirical and theoretical. When I was here studying physics, it was about computational being the new way to do science. It was about being able to do models, especially on quantum physics, that we could never have done before, and being able to make predictions both there and astrophysics as well, to be able to make those predictions based upon the computational horsepower we never had before. And they were based on physical models, equations, and the like. We now have this fourth paradigm, data exploration, data science. And it's a lot more about accumulating data and being able to make rationalizations and generalizations and hypotheses about the data coming out of the data, as opposed to putting a simulation together and doing some simulation of a complex phenomenon. So it's, this book, The Fourth Paradigm, makes the case that this is a new way of doing science. And many other folks have now come along with this phrase, data science as an umbrella, as to where it might go. And so what do we mean when we talk about data science, and what do we mean by geospatial data science? So focusing in on that. So as mentioned, I've been involved with Professor Wang for a while, and in particular, when he first got involved with the CyberGIS stuff back AAG in Chicago 10 years ago or something, I don't know when that was. And you have progressed the concepts much further with respect to where we're now going, perhaps with this GSI, Geospatial Software Institute concept, and hopefully that comes to fruition as we move forward and the like. And so, what is geospatial data science? For me, this is the topics that are most relevant. I don't pretend this is an exhaustive list of what geospatial data science is. I wouldn't put that forward that way. What I'm going to tell you is these are the topics that we're working on in OGC in an open standards environment forum that match that definition of geospatial data science. So we've got increasing data sources and volumes, right? We all know the data explosion. It used to be petabytes were big, now exabytes are kind of big, maybe not as big as they used to be, right? The number of sources of data, in situ and sensors everywhere kind of stuff. We'll get into a discussion about that. Geospatial coverages and analytics. As I mentioned, coverages is a term for a standard that exists for a data structure in geospatial, and I'll describe that and its value in things called data cubes and analytic-ready data. We'll talk a little bit about analytics. Mostly gridded data. It's gridded data, right? It's raster data, it's satellite data. It's what got me involved in GIS, was how do we make the transition between raster data and the remote scientists and GIS guys. Maybe they actually could talk to each other. That was a big deal back, a few years ago. Anyway, semantics and linked data. So we need to treat a discussion about that. Obviously, cloud computing is a tool set that has made a huge difference for data science. The capability to scale and the like is very critical to the things that we consider to be data science. Finish off with machine learning and some predictions about the future. Always risky to make predictions, especially about the future. So that's kind of the agenda. Progression of geospatial information. It used to be, in particular in GIS, regional centric, getting state maps, land cover maps, what have you and the like. Features as a concept and a GIS concept, and all of that technology that was developed in GIS capabilities and databases around feature management and the like. Very powerful stuff. Human-centric, being able to address that, being able to trace individuals' activities over time in particular. And then moving now to device-centric. You've heard the phrase Internet of Things. Every device, innumerable number of devices are connected to the internet, are giving us information, have a location, and are redefining what we understand to be the scale and the density and the availability of geographic information. So that's one perspective on that progression. This is the numbers, right? There's wild projections about the number of internet-connected devices, but this is absolutely coming true, and people are investing lots of money to make this happen. We are developing the protocols for making that transition to internet-connected devices, being as simple as web pages. So some of you may have experienced when that Mosaic list came out, when the Mosaic app came out, it had 10 websites on it. Some of you may remember that, maybe others do not. They weren't even born yet, right? So, but in any case, you know, that's the kind of scale that will, this scale will exceed that, right? More sensors perhaps, and no. So lots of sensors, lots of connected devices, big opportunity. Urban models and sensors and applications, so this is continuing to amaze us. We now have easy access to the footprint of every building in the United States. I can walk up with a USB stick that has a feature model of the footprint of every building in the United States on a USB stick. It's just, you know, done, it's available, it's working. Cities see 3D models as a key resource asset for their infrastructure management. Much like orthophotos were the base maps for GIS, 3D models are becoming the registration place for data in the city. So much like when you stacked a bunch of layers together in your GIS, you trusted the orthophoto and said, okay, the lake is there, I'll give it the lat long that's on the lake. That kind of registration is now happening, if you will, with 3D models. I want to know where that sensor is. Well, I know it's on the corner of that building. The 3D model tells me the corner of that building has this XYZ, therefore I know where that sensor is. That registration function in cities I see is being provided by 3D models. Scale of this, there's now people that take satellite digital globe type data, turn it into every city in the globe with a tin model of the buildings at a scale that's amazing, right? I mean, these are just huge data sets that we have just solved all of the IT issues associated with that. And they're not just visualization models, but these in particular that are based on a standard called CityGML and OGC. You click on that building, you'll find out information about that building. You'll be given a list of attributes about its tax record, about its occupancy, you know, all of the history, like the New York City Open Data Portal information is tagged into the CityGML data set. It becomes the reference point for all the data. So huge moving forward kind of thing. So, and then of course, the huge amount of remote sensing, climate, weather observations, huge data sets growing and growing. Like I said, the data set, the program that brought me into to Washington, D.C. in the 90s was all about Earth observation data. MODIS, MISR, Terra, Aqua, all the rest of those CloudSet now, and continues to grow, just amazing. And then of course Copernicus with some of its scale, they're easily at hundreds of petabytes and beyond. And that's even small data when we talk to some of our folks in Hollywood and the like. So okay, so how do we handle this stuff? That's the problem. That's the scale. What do we deal with it? One is going to be geospatial coverages. So as a concept, a coverage is a data structure. It's a mathematical concept that says, if you tell me a space, I will map that, a location in space, I will map that to some data value about that location. So it's treated as a mathematical function, mapping from the spatial domain to the values range. And it came out a lot of GIS research back in the 80s and 90s kind of things, which has become an international ISO standard and then has become the basis of quite a bit of our access to data. It comes in terms of continuous coverages, which may be a predictive model, may involve interpolation, returns of value at a point, or discrete coverages is probably what's more familiar with it. So this is raster data, right? This is grid data. This is imagery data. This is the way that I can get my remote sensing friends to talk to my GIS friends because we've got a data structure that both of them understand and can map between. So geospatial coverages as a way to model that. Of course, analytics, the key first step is data representation so that you can actually do something with it. Representing your data in a way that supports analytics is a lot about what coverages is about. One recent trend in that area is something called geospatial data cubes. Data cubes are not new as a term, but this the application and the technology to be able to take, for example, a set of remote sense imagery, Landsat or otherwise, with a time history, and then be able to do spatial queries down a pixel to say water presence, for example, yes or no over time, be able to do a time series based upon a pixel in Landsat by a single extraction out of that geospatial data cube is a very powerful, efficient access, and then analytics. There's this term thrown around called analysis-ready data, and it's trying to move all of this remote sensing data to become more a product that users don't have to know intimate knowledge about, but it is described in a way that they can make use of it and then do analytics on it. And so, you know, we've defined a set of data cube concepts, how to define a data cube. We have prototyped federations. We're working with a group called the Group on Earth Observations that manages the global Earth observing system of systems, about putting together a federation of geospatial data cubes, which will then support analytics to be able to do you know, key science and policy questions based upon this data. So, you know, that it brings us to what is analytics in this mind. So the easy part of coverage is the gridded data part, the domain part, right? We can write down the mathematics about what do you do for subsampling, subselection, you know, pulling out a polygon of data values and the like. We can pull every 10th data value and pull them out. We can do all kinds of really mathematically rigorous things with the domain side, if you will. We do not have a very good vocabulary about the analytics side. Because we don't have really good agreement about the definition of parameters that come out of our remote sense data. We are having this discussion about climate data records, Earth data records, essentially the definition of well-defined product names coming out of remote sensing. That will then support analytics, the ability to make a question that answers like what is the phenology of a plant based upon an Earth data record. Those kinds of questions in a way that somebody that knows GIS and doesn't know remote sensing should be able to happen in a commodity kind of basis. That's what would be good to be able to do. That's where we're not at. We've got, there was an AGU presentation last December, it was really good. We've kind of had data cubes version 1, which is really good on the one kind of analytics, the domain analytics. We need data cubes version 2, which is analytics on the other side. So this is really a research question. I'll come back in a couple of years and your group will have it answered, shall we? I'm sure of it. So moving on in terms of the power of what we're able to do based upon open standards, we have recently standardized the results of some additional research that has come out under this term discrete global grid systems. So discrete global grids are a sphere or an ellipsoid on which you tessellate that surface and then you allow that to become a uniform way in which you organize your data. And there's a variety of ways you can do that. The standard that we have recently published kind of gives you the rules, but there's whole classes and families of discrete global grids. And so we're now at the point of describing, using that vocabulary in the standard to be able to describe grids that people can interoperate on. So one of the first choices and the first criteria is what is the cell shape that you use to tessellate a sphere? It's even a little trickier on an ellipsoid, but let's ignore that for right now. It's a whole fun discussion. But you know, so there are three, right? There's squares, there's triangles, and there's hexagons. These are the three primary shapes, geometries that you can use to tessellate the surface. You also then worry about resolution pyramids that nest nicely. And then you put an index on it. You use some kind of a space-filling curve or some other method to define an indice that allows you to do really fast processing and access based upon, say, a 1D index on a 2D space. That's really important in computer science. It's really important on speed. It's really important on analytics, right? The problem is, well, the top part is math that's been done for a long time. the bottom part actually has some patents associated with it. And so there's a whole discussion about whose index do you want to use. Gets to be an interesting discussion on the intellectual property side of standards that I won't touch much on, but let it be known that intellectual property and open standards is an active discussion. Another example of standards-based research standards coming out of academic research and moving forward is moving features activity. So we have a very good conceptual schema for moving features. It's an ISO standard. It gives all the terminology and the like. We've now turned that into a rather robust encoding standard in XML, JSON, CSV, and that kind of stuff. And that's really cool. But what's really cool is it allows you to ask these questions in a uniform fashion. We're really talking now about space and time, 4-dimensional queries. And so where we've had really good, if you know the simple features standard from OGC, one of its real powers was what's called the 9-intersection model. It was a really good way to describe overlap, touches, fully outside of all those topological operators that got standardized, Eigenhofer sometime back, right? You guys know these people better. John Herring, though, is the guy that I know that's involved with all this. Max Eigenhofer, yeah, right. 2D, there's some 3D models on it, but this is 4D. In time in particular, the terminology associated with time. One question is posit a geometry and how close or intersects, but what even more kind of interesting is 2 moving features and being able to ask a software engine to tell you when they were closest, right? You can do all kinds of analysis to figure that out, but if a database would tell you that with a simple query, wouldn't that be nice? Well, it is nice, it works. So that's some fun stuff. So those are some more kind of gridded and feature-based geometry. Now we move to semantics and spatial semantics. So all of this knowledge web representation kind of on the upper right describes zones properties. Those are geospatially independent. But now we have defined spatial topological relations and put them into the terminology of semantics. So RDF, OWL, and Sparkle are the web technologies that allow you to do those kinds of things and then make questions about semantic logic relations and the like. I'm still this is not as exciting yet because I don't think it's reached its killer app stage yet, but somebody will tell me I'm wrong and they'll argue with me for a long time, but I'm still waiting for the exciting part to come out of here. But we've done some really good stuff, I think. Observations and measurements, tying features of interest to observations is one of the ways to really tie that down in terms of making the knowledge web and the semantics and the like relevant to geospatial. We've defined an open standard called observations and measurements, and that tells you how to take the action of a measurement and semantically model it so that you can do analysis in a GIS and the like. That's become now a joint OGC and W3C standard in OWL, and it defines the relationships between sensors and observations, actuators, actuations. We also have moved that temporal stuff into a joint OGC and W3C around temporal relationships and interval algebra. That's a W3C recommendation. So lots of good techniques, kind of from the data modeling, data representation point of view, the spatial operators, the spatial modeling point of view. But what really has made a big difference, of course, in data science is the compute capabilities associated with, in particular, HPC and cloud computing. And so this is what really justifies the scale up of large data, the ability to handle those large data sets in clouds, and then using some very powerful languages, Python and R. So we have attacked this cloud computing first, and then we'll talk about kind of machine learning and the like. Cloud computing is a wonderful thing until you found that you put all of your data in one cloud and you're never getting it back, right? And you might not even know what the cost of using that cloud is, right? You may, so our approach as an open standards consortium is to say clouds are wonderful. Wouldn't it be nice if you were not locked into a single cloud provider? What are the basic use cases that you'd want to have about cloud interoperability, about application portability, those kinds of issues that would allow you to take advantage of cloud computing without being locked into a single cloud provider. So the two actors in those use cases, one is an application developer, the other is the application consumer. So that's a software writer, right? And this is somebody that's going to use your app. These are the kinds of questions that use cases that we've been addressing, and we've got initial results that are being deployed now. So how to dynamically register a new app. You put it in a container. How does somebody else come to know about your app has been deployed in the cloud and make use of it? What is the open API on that app that allows them to use your container? Those kinds of questions. How do you minimize the app developer's effort with respect to containerizing and the like? And in that regard, with respect to containers, OGC is going to make use of the broader cloud computing infrastructure capabilities and specialize it to geospatial. Consumers use their own data. Another way to say this is computing is close to the data. So you move the compute to the data as opposed to the data to the compute. Dynamic scaling a cloud environment, the real key reason that these things are very valuable is that Amazon has way more compute power than you could imagine. I get astounded every day at the statistics, but and then cloud interoperability via open standards. So this whole discussion about avoiding lock-in regularly for me comes back to, or for us, comes back to what is the open standard that's needed to avoid that lock-in in any given market. And so that's what we're doing here in cloud interoperability. So here I introduced some of these terms, acronyms earlier, but this is the deployed architecture we've been using in our testbed environment for interoperability and portability between clouds using OGC web services, multiple cloud providers. Essentially, our web services were designed to do compute near the data to begin with. It was always assumed that there would be a lot of compute capability on a WCS, for example, web coverage service, to be able to do down selection, subsetting, subselection on the data and only give you what you need. Portrayal is huge processing. Web processing service and web coverage processing service, and defining the analytics that go along with this is still a challenge. We've got the container that says describe your analytics, but we don't have the good semantics for describing analytics. And remember what I was saying earlier about you could talk about subselection, subsetting real easily, but how do you talk about analytics on the that the user would care about from their data? That's all kind of still tied up in this defining your algorithm within a web processing service. Okay, so machine learning obviously is a key topic for data science. We're actually probably on the third generation or so. People talk about the third or fourth generation of machine learning, neural networks and the like. And the driver here, what really made a difference was cloud computing, allowing you to scale neural networks like you never could before. When I was studying neural networks as a control system engineer here at U of I, we were talking about neural networks that had 10 nodes, 100 nodes. And so what is TensorFlow now? Tens of thousands of nodes, or that scale of thing, and the compute power that goes along with it. It's made a huge difference. And in an imagery point of view, a lot of it points back to this paper on CNN's convolutional networks, a KSH paper in 2012 that won this competition called ImageNet on classification. It just blows everything away. It's still kind of amazing to me, given what I knew. It's always fun to be amazed by technology. It was a problem that couldn't be solved, and now you turn around and somebody's just dead solved it, right? And that's what we need to do. That's what technology needs to do for us, right? It makes really hard problems just go away and turn into things that are really good solutions. The challenge is trying to understand what machine learning is, right? What it does, what the provenance of those are, because what you do with a machine learning algorithm is you train it. You give a set of data and it will learn the data and it will tell you something about the data, and then you apply that trained model to something else and you trust the results. And if you look under the hood, what you'll see is 10,000 nodes with weights associated with them in a graph, and you have no way to really understand what that means. And very bright minds about this have been fooled, and there's some really good examples, in the media now with respect to provenance of machine learning and what are we going to do about it kind of stuff. So technology solves problems. It also it creates unintended consequences that we need to figure out how to deal with in our technology and policy. What we're doing in OGC with respect to this is, a lot of what we do from a standards development point of view is based on prototyping. It's let's get a bunch of good developers and geographers in the room, have them work out a solution, and out of that good solution, something that works, that's where you write the standard. That's what you base the standard on. Running code wins in that respect. In the standards program, it's consensus, right? We all got to get around and agree that that's a good spec, but the genesis of that idea usually is running code wins, okay? We're doing that now with machine learning AI applied to geospatial data. We're looking at all kinds of coverages and discrete vectors and data streams, applying machine learning and artificial intelligence to that, seeing what difference it makes that it's spatial data versus non-spatial data, because a lot of these techniques were non-spatial techniques. And so, how to apply that and how to understand the semantics when it comes out. So that's the current activity that we're working on. Kind of in this last few slides, let me try to reflect, right? So you get invited by an esteemed professor to come back and speak at your alma mater. You ought to be able to reflect a little bit, right? Let's see what happens. So Douglas Engelbart, anybody heard the mother of all demos? This was the guy at Park in it was 50 years ago. He did this mother of all demos in San Francisco, and it had the mouse, it had Windows, and it had network communication, it had voice over whatever they had at the time. It is this incredible demonstration that Engelbart did back in 50 years ago. In any case, he wrote a bunch of other good papers, and he said human-machine partnership is probably the most critical way to go. We have a feel for, we're really good for intuition, but electronic aids would be helpful. More recently, Walter Isaacson, 2014, did a history of innovation in the digital revolution. Perhaps no matter how much faster computers get, the combination of human and machine is probably where we're headed, trying to understand what the machines are telling us and making use of that. So I recommend this book for folks that are, especially if you're just starting off on your career in terms of leaving here and going off in research or industry and the like, to understand a historical perspective of this digital revolution. Most successful innovators had one thing in common: they were product people. They cared about, they deeply understood the engineering and design. A lot of times we talk about innovation as it's a business center where you go to and meet other folks and you learn how to do ROI and investment and the like. This book makes a really good point that the key to innovation and the most innovative products were that was led by the folks that understood the design and the engineering associated with that. There's obviously business associated with it, but it's the people that understood the development of those products that made the most difference. The other is that in a digital age may seem revolutionary. It's based on expanding ideas. It's amazing how much, there is no single inventor here. Every now and then somebody has a really good idea, and we find out that other people have also kind of had that, and it builds and it builds and it builds. It really is a social experiment. So let me finish off with some predictions about the future, right? So we maintain a technology trends prediction capability. And this is, best guessing kind of thing with some magic put in, right? So we do a landscape survey and identify everything we think might be relevant. And we organized that into 8 categories, and this is all on the web in a GitHub repo. You can find descriptions of each of those. The summary then gets into this kind of perspective. So this has 2 axes. One is the time horizon, and the other is the effect or impact, I guess. So after next and next, right? And we're now, next, and after next is the horizon. Not sure what the time scale is on that, but it's kind of the sequence. And then sustaining and disruptive. Disruptive means that the marketplaces will be different once that technology comes out. And then there was kind of a consensus drawn up on which of those are probably the most important. And obviously this is from a specific group at a specific time. But so take it for what you might. But these are areas that for sure will make a difference about geospatial data science over the next 10, 15 years kind of time frame. So I leave you with that. It's a big picture view, right? How about that? So that's what I have on data science analytics. So, thanks. I guess we have time for questions if there's, yeah.
It's quite good. Yeah, we do
Dan.
have plenty of time for questions. Raise your hands and Dan.
I was curious on your last slide that showed these trends.
Yeah.
I was also thinking that you could put a number of these trends on a hype curve. And
Yeah.
I was wondering if you've tried to go back and look at if the trends that you were thinking were going to be the future 5 years ago actually would follow a hype curve.
So if you go to that GitHub, you will find a page for each of these trends. And on that is a field that says the Gartner hype curve. And it has a place to put that. And we started that approach, and then we have research in the geospatial domain out of Nottingham, that says knowing where you're at on the hype curve is not predictive of where you will be in the future. So we kind of said, that's what you want it for. I mean, we understand that, it kind of makes sense and the like. So we have not followed through on that for that reason. So, yeah, but the Gartner hype curve's interesting, the valley of despair, right?
Predicting future is hard.
Predicting, all prediction's hard, but the future's there, right? Cool.
Other questions, comments?
If you want to take a look at our standards, one thing we do is make them freely available. Anybody? We have no license costs or anything associated with them. Yeah.
I guess I was also curious about the cloud standards that you were talking about and the fact that there are a number of other groups that also are providing cloud standards and how those then mix if you try to work with other groups or if you try to do things that are really specific to the geospatial community.
So we have alliances with about 60 organizations. A big part of my day is working with those and being the gatekeeper, if you will, promoting those connections. With respect to cloud in particular, there is what's called the Cloud Native Foundation, I think is what it's called, it's not geospatial, it's about containers. There's actually 2 or 3 of those kind of consortia associated with cloud computing. And we are tracking, working with that kind of thing. And then our role is to how to do geospatial cloud native. The other is kind of the non-institutional standards development. So in the wild standards development, for example, there is a cloud optimized GeoTIFF, for example. So GeoTIFF is one of these specs. It's been around forever, as we know, has a JPL roots. Some folks have defined a cloud optimized version of GeoTIFF, and it's written out there as a spec on a web page somewhere with a bunch of really bright software developers that are saying, do this, do this, do this. And so another part of my day is working with that kind of open, in the wilds community, if you will, to see if we can take, say, cloud techniques that are in that community and bring them into, because a lot of our members want something a little more stable than a web page and some part-time developers. And so that's what our role is, to kind of create that. So, and then, a lot of different cloud technology, open source. I didn't speak much about open source here, but it's probably worth talking about the distinction. I always make this distinction between open source, open standards, and open data. There are three things that are different that go well together, right? So open source is the code, it's software to code, and you might have multiple projects and the like that are developing code. And there's repositories and ways to promote projects with an open source. There are several foundations, open source foundations on Geo that we work with, Apache being a key one. So that's open source. Open standards, obviously what we do, it's a specification of interfaces or encodings that are available for anybody, that's not dominated by a single vendor. So people will say, vendor A will say, I've been using this spec for a while and it's really good, so I'm going to make it open, and they'll put it out there on the web, and yeah, you can get it. It's public. But it's not open in the sense of if you invest in that and they decide to take it back or change direction, you have no control over that, right? So open specs, open standards are what we work on. And then open data. Open data is, the ability to get that data typically for free. And knowing any encumbrances associated with open data has been a big push as well. Those things work well together. We don't have a stance on any of those except for open standards. We think those are the best. Go figure. Yeah, Dan.
Sorry, so just to add one more,
Yeah.
Open community is maybe another thing
Open
we're thinking
community.
about.
What do you mean by that?
So you could think of open source as that the source code is available,
Yeah.
and you can read it, but it doesn't mean that somebody's actually going to take your changes if you want to give them back.
Absolutely.
Versus open community, which is more a governance model that I think maybe goes with some of the open standards versus the vendor.
Well, it certainly relates to these, say, Apache, OSGeo, and Location Tech, which are communities. They have working procedures and the like, and they also have really long debates about what is the governance model for open source, as to whether you're supposed to be, take all comers, or whether you're allowed to be kind of a dictator about your code. Those debates happen there, but they all kind of define that. And very interesting. I mean, somebody must have already done the social studies on open source development. I don't know what the conclusions are yet, but it's good stuff. I mean, open source is really valuable stuff. So, yes, sir.
With all the crowdsourced spatial data now, has there been any discussion about some kind of privacy standards?
Lots of discussion. There's privacy and there's security. We actually at lunch had a little bit of discussion about this. We have security standards, that is access to the data. For example, role-based access to feature level or attribute level. Those are existing standards that we do, but what you're really asking about is privacy and individual personal identity. And
some of it's individually identifiable, but some of it's kind of could be implied, even implied relationships.
Yeah.
That might be concerned about.
It used to be, there was always this discussion about, we'll de-anonymize this. There's a better word for it than that. And what I've seen lately is I don't think anybody trusts those anymore, right? I mean, you've seen so many examples. The taxi cab data set out of New York City is one really good example, right? Where they said it was going to be completely anonymous or whatever. And they've been able to say, well, actor A didn't tip their cab driver after this late night binge. They got that data out of this anonymized data. So I don't think, where I think it is a technology issue. We have the ability to control that data. Do we have the policy interests to do that? Obviously, that's happening with respect to social data right now. There has been little, companies have seen the value of using that data for whatever purposes, and they have been unrestricted in doing that. Is that going to change? Maybe. Maybe. We were talking also at lunch, one of the key things about the future, we're all familiar with we have a score for our credit score, right? Some people, may remember when you didn't even know who those scores came from, and you had no access to your credit score, right? We now anticipate that based on, devices like this that track data, I'm sure it's already happening, quite frankly, people are getting individualized risk scores. So the index, you have somewhere out there already, I'm sure, at least for me, because I share everything it seems, there's a score about my risk associated with where I go and what my heartbeat is and all those kinds of things. And that data is being sold to, or will be sold to, insurance companies, already is being sold to insurance companies. And we don't know who those companies are. We have no access to those companies. And it took laws in Congress to give you your one, access to your credit score a year. That same kind of, I see a parallel with that on credit scores to these privacy scores about your personal behavior. You're going to end up find out about that. So it's probably already happening, right? The future's already here. It's just not widely spread. Yes.
I would think that those kind of questions come up if you're having conversations with social scientists. You're talking about, this is geospatial, but, obviously there's a lot of uses for it. And social science data tends to be a lot messier. There's a lot of things we haven't established: interoperability, reproducibility, all those sort of things. So what kind of conversations do you have with those folks when they arrive?
We have just established, we have a bunch of working groups, right? And for different domains, and we just established a statistics working group, which I anticipate will include discussions about those kinds of topics. Now, whether or not we are the right organization to do policy recommendations about privacy and the like is an open discussion right now in the consortium. There's some of us that think we should be more proactive in at least identifying the issue and what are the options. We don't have any power to set any, we don't have any power to require people to use their standards, and we don't have any power to require them to follow any policy recommendations. But the first part of that education and step and policy formation is recommendations to be considered, say in a social science and statistics setting and the like. So if that's of interest to you, I welcome you to come join the discussion. So.
Also, very quickly, I just put the screen up differently than George's slides. The next speaker in this distinguished lecture series is a social scientist coming to discuss the kind of questions you posed. So mark your calendars accordingly if you're intrigued by this set of issues. It's March 11th. Should be quite fun to.
That's a very interesting topic.
Yeah, deep dives.
Come back to that.
So I had a related question, George. You touched upon this, which is, I think, critically important about the ethical aspects of the movement into machine learning and data-driven innovation discovery. So, for instance, you had a slide about your process of getting to the sort of machine learning analytics, and oftentimes when scientists employ these techniques, it's very much black box. Once it's baked, and the liability and the trustworthy and the repeatability, reproducibility, all these issues. So what do you see, broadly speaking, we're going to tackle this black box?
Yeah, right, right.
From not only making science happen, but even ethical considerations. Is the science in danger even in this regard?
So we have certainly had discussions that are under the topic of provenance of machine learning, where provenance meaning, essentially how did you come up with this answer and can you trace it back and repeat it? Repeatability, which certainly gets into the science topic, it ought to be repeatable and the like. And so to look at the technologies that allow for that, we do not. I would say we, OGC or the machine learning industry, have there's no real good answer yet for that. And what we have seen is, in particular, government agencies and professional societies taking action. So, for example, ACM has a policy on machine learning and what you should and shouldn't be concerned about. New York City has an interesting task group right now on machine learning applied to resource allocation. It was almost an edict, but they said, we don't know enough, so let's turn it into a task force to study. But the edict was going to be for any city resources that are deployed using analytics. I don't even know if it said machine learning, some analytics is the way it was phrased. You need transparency into how that was done, and you need a diverse working group associated with the development of those analytics. And there was a third one associated with that. I forget what the third one was. But in any case, you can see where the policy setters are saying, we know we need to, because we're being asked by our constituents, why did the snow plow go over here instead of over there? And based on the analytics is not a good enough answer. There's got to be more transparency and defensibility of those resource deployment decisions. And so that started at the middle of last year. And so it's about time to check back and see if that task force, what they're doing. So that'll be interesting.
And I also see there's a growing digital divide because increasingly the capabilities are operating at a scale of very majority of scientists and users do not have access to repeat or verify what's going on.
There's a lot of different divides. One interesting divide is the pace at which somebody who is not a digital literate like myself, having to keep up with the folks that were born digital literates and essentially learned to code in grade school, right? And so, the ability, I would think every university student that comes into this university has written a line of code at some point. Do you think that's true these days?
And in fact, we have a movement on this campus trying to make that as a de facto.
Really? Yeah. Good, I applaud that.
Good.
Yeah. Because so much of what we run into in all of our daily lives is based on understanding how computers work, and if you haven't done code, you don't know that. So understanding the model world is kind of dependent upon having some literacy, code literacy. And so Illinois is at the forefront of that?
Is trying to, stepping up to understand how to make that happen.
Yeah, okay.
So that's the whole data science education movement on this campus.
Yeah.
You
Can
got
I ask a question
comment?
about that? So there's a campus-funded project initiative on campus right now to develop K-12 computer science education for the state of Illinois. There hasn't been such a
Okay,
thing, but it's
okay.
being instituted. There's legislation that's going to go through the Illinois legislature. The Chicago Public Schools have made that part of their criteria for graduation. But where could those people hook into? Is there a working group for that?
Yeah, right.
But I mean, it's important, so do students coming here have they had the experience of writing code, and so they're thinking seriously about what that means, this basic citizen literacy.
We've engaged in a variety of hackathon and code fests and the like that occasionally involve K through 12. Probably not as much as we would like. Our members are a bit more interested in what have you done for me lately kind of thing. So we do not have that remit as much to look at the future education workforce as maybe we should. They make a good point. So I don't have a working group for that right now, as a matter of fact, but you make me want one.
Major challenge.
Yeah,
And also
absolutely.
opportunity for universities to tackle this because it's changing very rapidly.
Yep. I've had we had a project with the Department of Homeland Security, and so we did a hackathon associated with it, and it was interesting because the government agent who knew it was going to be, a bunch of people writing code said, "Oh, well, I'm paying for that, right? So give me all that code." Like, I'm not sure that's what you want to do. To request that hackathon level code is considered to be part of something, a contractual mechanism. This may be out of school, if you will, for this discussion, but I think it points to the fact that the way some folks think is through code, not through, for example, writing requirements. in an engineering process. They write down and they write code and then they show you and it's hard to educate, say, procurement officers and others about how in-depth, how integrated code development is to that set of developers that we work with. So,
And in our case, how to turn geospatial knowledge into that coding process,
mm,
right? So it's not just programming, but intelligent geospatial programming that would be tailored to important problems, you know, that could have
Absolutely.
ethical implications and so on. So how to fuse those two aspects together,
mhm.
I think it's going to be very interesting but challenging, very important to deliver.
Yeah, interesting future.
So I think in the interest of time, we want to wrap up.
Okay, yeah, good.
Let's give George a big round of applause.
Thanks, thanks.
And we have a small token
Wow,
of
that's-
appreciation that has your name and the
Very
series.
good.
And most
Yep.
importantly, a globe. Yeah.
Thank you. Thank you
Thanks
so
very
much.
much.
Yeah.
Yeah.